Yeah, thank you very much, Henrik, and thank you all guys for attending this session. I'm really glad to be here. So as just Henrik said, right, my name is Denis, and I work at Intel in a compiler team. So essentially, our team, has a huge focus on performance, and specifically on performance of applications from the CPU perspective, right? So we as a compiler developers, we try to generate, the best possible machine code from your application, right? So it will be run faster, right? But in today's talk, I will be, I will discuss why you should become good at optimizing your code, right? But don't worry, it won't be too low level. There will be no assembly code whatsoever. So this will be still pretty much high level. So let's jump right into it. So our world generates just a huge amount of data every day, right? So we generate over 1 million terabytes every day, right? And this number keeps growing at a rate about 25% per year. So all this, this fuels the need for processing this data faster and faster, right? Unfortunately, modern CPUs are not enjoying, the same speedups as they used to during the past decades, right? So if you look at the chart, you can clearly see that performance of a single thread, of a single core, is definitely, slowing down. It sort of, reaches a plateau. And it used to be the case that, some software vendors, they were relying on hardware to provide performance improvements. And they did not necessarily spend human resources themselves, right? Rather, they relied on hardware for providing those speedups. Unfortunately, the easy ride for them is over, and they must spend, and they must pay more attention of how their code actually runs and improve its performance, right? And this is actually what John Hennessy said in his Google I/O 2018 talk, that the general purpose computing is dead, right? And it's now the time of specialized hardware. And this is, not just a future, right? This is already a reality, right? We have a whole bunch of different accelerators in the world. But if you look at for example, at the software side, right? If you take a look at the compiler, it's not promising either, right? There is actually a Prosthetic Law that says that, compiler advances double computing power every 18 years. Okay, so it means that the code that the compiler generates gets faster. The speed of the code that compiler generates doubles every 18 years, and or maybe even more than 18 years, right? So and there is a recent paper called "There is Plenty of Room at the Top," which tries to to identify the key areas where we will what will be driving the performance in the nearest future. And so they identified 3 areas, and one of them is hardware architecture, right? So and as I said, right, we already see this coming. We have a whole bunch of different accelerators. And in the future, we'll have even more specialized hardware, which will be built for particular workloads, right? Like video streaming, like compression, like image processing, and so on and so forth, right? We have a whole bunch of accelerators for visual processing, for neural networks and stuff like that. The second area is actually algorithms. Well, you might be surprised, right? Like, well, what's new in algorithms? However, there are still, some areas where the research is quite active. Machine learning is just one case. But then actually also the AI, the artificial intelligence, can play a big role here, right? Since artificial intelligence can invent new things, new algorithms to existing problems, right? New approaches. And this is actually because the AI, explores the entire computation space. It does not reject any crazy ideas. That's why AI is capable of finding new algorithms. And then the third area is actually software, and this is the area where we as software developers can make an impact. Okay, so this is the software tuning, which I will be talking through the rest of my talk. So during the post-Moore era, it will become ever more important to make code run fast, and in particular to tailor it to the hardware on which it runs. This is again from the same paper called "There's Plenty of Room at the Top." And actually, so also in that paper, the authors are showing this interesting table, which summarizes the results of performance engineering of a naive matrix multiply kernel written in Python. Okay. The reason why I show this slide is actually not to pick on Python. Okay, I like this language. I write Python myself, but the reason why I provide this slide is to show that the software is not optimal by default. Okay, and those kind of improvements that are on the bottom of this table, right? So, for example, using specific hardware features, right, to speed up the program. This will be the areas that more and more people probably will be paying more attention in the future. Well, and you might be asking, why should I care? Why CPU does not solve all my problems? Why compilers do not solve all my performance problems, right? And well, to some degree, that's true, right? CPUs are great at, let's say, at crunching numbers. However, all those computations. So, for example, CPUs, they're great in crunching numbers. However, when it comes to more smart decisions, they are unfortunately just silently execute the code that you told them to execute, right? So, for example, when you wrote the bubble sort, right, the CPU essentially is helpless, right? It cannot transform your badly written algorithm to something better, right? Then compilers. Compilers are great at eliminating unnecessary work, right? However, when it comes to more complicated decisions, like for example, like function inlining, loop unrolling and vectorization, they usually rely on some sort of a cost model and a whole bunch of heuristics, which are not optimal by design, right? So this all leaves the room for tuning our code. So again, the message of my talk is that it's become prime time again for software programmers to get really good at optimization. Okay, the free lunch is over for us, and and those are just some of the examples from the giants, right? From Google and Yahoo, that shows that still even a small improvements can make a drastic impact, right, on some of the companies in our industry like Google and Yahoo. And so, what can you do to prepare yourself for the future? Well, and first of all, learn your technology stack, right? Learn where your application stands in the technology stack. What components your application is utilizing, right? It will definitely pay off in the future. And know the limitation of each of the stack, right? So, for example, if your application is a heavy CPU has a high CPU utilization, learn about CPU microarchitecture. Read basic assembly code, right? If your application spawns lots of threads, right, learn about how you can tweak the OS scheduler, right? Learn about CPU affinities and and in terms of compilers, right? Learn about the compiler optimizations and options that are available to, to control them. So yes, I agree. A lot of performance gains will come from the application code itself. But also, when you squeeze, the last bit of performance from your application, you actually want to start, looking at the lower layers, right, and how you can tweak those. So the second point is avoid performance traps. And the number one performance traps that I see is, that people make predictions about the performance of their code. And this is just wrong, right? So it's modern systems are so complicated. It's essentially impossible to predict how your code will run. So do not guess, always measure. The second trap is that I see is that people make changes with no impact, right? So the example here is that, people, for example, change I++ to ++I all over the code base and hope that, it will magically speed up their program. However, in most of the cases, it's just a wash, right? No impact on performance whatsoever. So the number two trap is, do not rely on your intuition, right? Rely on careful performance analysis, right? On collecting specific performance metrics and, and interpreting them in some way. The trap number three is actually I see, people optimize their code without knowing their data, right? So, and what they end up actually in with optimizing their application for some theoretical workload, which is not practical, right? So always know your data and optimize your application based on the data that it's working on. The next trap is people sometimes create a bad benchmark, right? So so they think that they benchmark what they want to benchmark. However, this benchmark actually benchmarks completely something else, right? So and this is actually a trap that is quite easy to fall into, right? So so when you're writing the micro benchmark, really, the small amount of code, it's really it will be quite beneficial to look into the assembly and verify that the benchmark really executes the thing that you want it to execute, right? And then the final trap is actually kind of funny. Do not blindly rely on big O notation, right? So the example here is that is that insertion sort is actually outperforms quick sort on a small arrays, right? So for some cases, in some cases, you shouldn't just go with whatever algorithm is known to be the best in terms of algorithmic complexity, right? You should not discard the hardware effects, right? The interesting example here can be a binary search, okay? So binary search, is a great algorithm. However, it's just horrible from the CPU perspective, okay? It is horrible because it experiences the high number of cache misses and branch mispredictions at the same time, okay? Well, why? Because the algorithms jumps every time either to left or right, right? And there is a 50% chance that you will go to each direction, right? So this is essentially a worst case for a branch predictor, right? For a CPU branch predictor, because it literally cannot tell where the algorithm will go. It cannot predict this. And also, every time you jump to a new location, this is pretty much a guaranteed cache miss, right? So, and this is actually why we have, as a dedicated layouts just for binary search, like, for example, Eitzinger layout. So I actually wrote a book, right, for software developers, which is called Performance Analysis and Tuning on Modern CPUs. And the book is dedicated, to teach software developers to find the bottlenecks in their code and optimize them and improve performance of their code, right? with specific focus on CPU, right? So the book is divided into two parts. The first part is the performance analysis, which talks about essentially how to find the bottlenecks, right? So it introduces it starts actually, it goes from the very basics of a CPU microarchitecture, introduces CPU specific metrics and performance analysis approaches like flame graphs, like checking compiler optimization reports, some hardware specific analysis like top-down microarchitecture analysis, and also pretty established one like roofline. And then the second part is actually all about tuning, right? So the finding the bottleneck is only a half of your job as a performance engineer, right? The second part is actually how you fix it, right? And this is sort of a beat the compiler game, okay? So where you rely on the compiler for the most of the cases, right, to optimize, to make performance improvements in your code, but you also control it with with special hints and pragmas and so on and so forth. So just an example of topics that I discussed, right? So this is a profile guide optimizations, how you can optimize your memory accesses, how you can utilize vectorization capabilities of your CPU, how to optimize the code layout of your application, how to eliminate branch mispredictions, and how you can discover all those opportunities. All right. So the book is actually available for free on my blog, which is easyperf.net, and it's also available on Amazon in print. Oh yeah, and then once you figure out the basics, you want to practice, right? So first, practice using tools, right? Learn what tools are available on your platform, right? So if you're Linux, so it's Perf, or you can also leverage some open source and cross-platform alternatives like for example Hotspot, and learn about great products like Intel vTune and Advisor. And then practice performance optimizations, right? So how you can do it? Just pick some application or pick your application that you're working on, right? Find the bottlenecks in that application, right? Profile it. See where the program spends time, and so on and so forth, right? Try to characterize the bottleneck, right? Is your application bound by memory? Is your application bound by computation? Is your application experiencing high number of branch mispredictions, and so on and so forth? And so I actually, on my blog, I also organize performance challenges, okay? And those are just some of the examples that participants were able to do, okay? So they optimized the 7-zip benchmark, right? Highly popular, by 12%. We were able to optimize the Lua interpreter by 5%, and actually, so the performance challenge that just ended probably a few weeks ago is about canny edge detection algorithm, and folks were able to optimize it more than by 2x. So yeah, I think that's about it from me. Thank you very much for your attention, and this is how you can find me. And I guess now we will open it for questions. I'm ready, and I'm happy to take your questions.
All right, thank you, Denis, so much. So could you maybe send yeah, so I see the easyperf.net, maybe because it seems that you have a lot of great assets on your blog, so maybe you can drop it to the chat for the community. It will be very useful. So while you're doing this, I will enable the webcams of the other pack members. So we have Mark Thompson, who is connected, John Bon Jovi connected, and we have Steen that is still connected. All right, let me change the view so we can see all the speakers. Here it is. Wow, here it
I
is.
just send the link to my book.
Awesome. Thank you so much. So before my questions would be on your. It seems that you said that you had a challenge. So just how this challenge is, how you structure that challenge. I want to have more details on this one because you showed some great numbers on the improvements, but I want to have more details on how people can participate to your challenges and so on. So that will be very interesting as well.
Sure, yeah, absolutely. So how it works? I just give the some workload to the folks, and then they just take some time. It's usually about 3 to 4 weeks, and they try to actually to optimize it, right? So they try to find the bottleneck, try to fix it, and then I just collect all the submissions and I evaluate them and publish the Discord table. This is how it goes.
But in terms of a solution provided by the community, usually are the solution quite similar, or you have completely different approaches, which is where maybe when you look at it and say, "Whoa, I never thought about this one." So
Yeah,
what is your
right. Yeah, it actually happens quite frequently, right? Yeah, and it's actually a great way to learn, right? So and for myself as well. So that's great when someone sends you some solution that is completely different from yours, and then you're like, well, wow, okay. So I haven't thought about that. So yeah.
That would be
Cool.
great to have a sort of a. Do you just more for my interest? Want to get all those results back, or did you thought about sort of organizing like a sort of not a webinar? I don't know how to name it, or podcast, and then you compare both solutions, and then you try to say maybe if you combine both of the solution, then you will basically reach out to that level of performance. So that will be very interesting for the community. Have you thought about doing this, or maybe you're already doing it?
Yeah, actually, so I only started doing this from the last challenge. Yeah, so for the last challenge, we actually had a Zoom call and where we discussed, with all the participants, what they were able to find, right? What are the the possible ways to fix the bottlenecks in the in the benchmark? Yeah, so that's essentially great. I don't have, I'm still thinking about, how I can package it into the form that, that will be more accessible than a Zoom call, right? So then, will be, more, more organized fashion. So that's still, is not clear for me how we'll do this. But
Gotcha.
that's a good point, yeah.
So you were talking about, I mean, C++. To be honest, I did C++ when I was a student, I think. And then so I don't know what happened, but then suddenly C++ was out of my scope and out of my radar. I don't know why. And it was replaced suddenly by Java, then Node.js and other languages. So you were referring to the C++ compiler, but I am mainly using Java. So have you ever done anything around Java as well, or is mainly on C++?
Yeah, so my book is actually targeted to native programmers, right? To the programmers in native languages mostly. However, some of the things are still applicable to managed languages. But yes, so to answering your question, I'm not talking about the garbage collections and and specifics of managed environments. So in my book, yeah.
All right. So I see that Stain and Lloyd and Mark is, I think, is in the back making some last-minute settings. I see him. So Stain, do you have any questions for Denis?
Hey, Dennis, great talk.
Thanks.
For me, it's yeah, it's so specific what you talk about. It's so technical, and I don't know if you listen to my talk. As always, I do speak about the primary measurement is the application performance, and say that they have SLOs or NFRs or whatever you call them. A web page 99 percentile should be under 3 seconds. And then I ask myself, how do you know how much effort you need to put in what you do to actually meet SLOs? Because you can tune forever, and it's complex what you do. So how good do you need to write your code to meet normal SLOs?
Right, that's actually a great question. Right, and so you see, I'm working actually in on compilers, right? And so
Right.
for us, for us, even like a small percentage, like half of the percent, can make a drastic impact. Well, why? Because this change can translate into something more impactful, right? Because in the end, our compiler will be running on the large code base, right? So and essentially all the applications in the world can benefit if you can from this small improvement, right, that you made. So we end up caring a lot about tiny improvements. So when you're talking about the application developer of right, and then of course there is a point of diminishing returns, and at some point it's becoming more of a business decision where you do want to proceed, where you just want to stop with optimizations because it's already good enough. So yeah.
Yeah, it's because triggered me because you showed that maybe also to get this question about Python, and then you had the improvements that you could make with different languages, and was it 60,000 times faster? It was a lot because I sent it to my colleague Joey, who is a Python developer, so he will love it. But it's what you say. It's the return of investment. If people write faster code with Python and that suits the application, then that's fine. But what you're doing is a different ball game, and there it's really beautiful what you're doing. But it's not for everyone, and it's also not needed for everyone. But what you do, absolutely. Talking about flame graphs, beautiful. Still complex, I find them. I think that we should think about something new and not just the flame graphs. They are outdated. We need something better, and we are working on it. And I think there should be something better than flame graphs. But yeah, it's very specific and it's very specialized and very well done.
Just one comment there about the easy way to get a 60,000 times improvement in the performance of your code is to start with really terrible code.
Yeah. That's your best client as well.
Oh yeah, the return on investment is amazing. Right.
So so you see that's not my table, right? So that's the table that I showed. It's actually from the paper, and I believe it's just a 3-line program in Python. Okay, so it's just a nested for loop with just only one statement in inside the loop. So it's a really naive program. I agree. Yeah.
Mark, in a 4K format, you can see that full HD quality. It's just amazing. So, Mark, do you have any questions for Denis?
Yeah, in particular,
I think I don't know which mic you're using, but you're pretty far from the mic.
Oh, well, here. Just bring this down in my face then. How's that? Is that better?
Much better, yeah.
Is that better? I can also crank it up. Is that better?
Yeah, it is.
All right. Oh, and now that thing moved to the thing of the time. Henrik, Jesus. So great presentation. I wanted to say generally, particularly OS schedulers and the idea that there are mainstream applications that are built in small little containers that run everywhere and bounce around between containers and bounce across OS level schedulers. To me, that's on the same level as being like file descriptors are hidden somewhere. Like, oh, that's that view limit setting. That's that weird set limit thing in the Linux world or whatever, it's like file descriptors can undermine everything you're doing from a socket perspective or whatever. Why is that a file? And I think schedulers is also that mystery thing. So I wanted to ask you, what platforms were you working with, and where do you see in a modern containerized world these sort of people really learning to master OS level scheduling and then matched application level schedulers as well?
Yeah, that's a great question. And so you see, this is actually also the level that I'm specifically not involved in, and I'm working on Linux mostly. And so you see, from the compiler perspective, we are working on sort of some code that is already fixed in stone, right? We essentially cannot touch the system calls most of the time, right? So we are only focused on the user level code, right, from the compiler perspective. But so I'm not sure what do you mean by what specifically you are asking about so how one can tweak the OS scheduler.
Yeah, well, it's just a general, what are your thoughts or commentary on people that are like, well, I'm going to run 100 different containers, and those containers are not that platform, a container infrastructure running across, now you can get a machine that has, 500, 700, 1,000 actual cores, virtual cores presented. And it's like, do I actually have that many OS schedulers, and do I need to tune for, say, a Docker platform where how many containers are spread across? I mean, do we just assume like the days of I need to be an expert in OS level schedulers, are those kind of waning in a containerized world, or were you testing in very specific, not virtualized applications running hardcore in Linux with direct access to the system calls of the OS level scheduler?
That's actually a great question. I don't have a strong opinion on that, and I believe that this is actually the reality that we are facing with, that we as developers, we are getting further abstracted away, right, from the real hardware, right? So because we on the top, right, on the application level, and there is a whole bunch of layers in between us and the hardware, right? So there's a whole bunch of orchestration and virtualization layers, and it becomes harder for us, for application developers, to reason about. Sometimes we don't even know, right, the hardware on which you'll be running on. So and then yes, that's a great question. I don't have an answer to.
No, I don't think there is an answer. There's an opinion, and it's beautiful. Like I think I agree with you, and I appreciate your experience for sure. Living close to the metal, that's always nice. So yeah, excellent presentation.
I think it's a new challenge of our century, I would say, or the new way of building apps, because we are all evolving in that environment. Saying Docker is amazing, it simplifies everything, but it brings other challenges. So Stan, you have a question?
Yes, Dennis. 2 questions. How did you actually roll into your profession, and how do you find young people that actually want to do what you're doing? Because I think that lots of people would be not interested in doing what you are doing.
That's true, and I think so. Well, I believe that at some point this will become more important. Okay, so the performance tuning will become more important. I believe in that because as I explained right in the beginning of my talk, that we don't get performance boosts from the hardware nowadays. So I believe more and more people should be forced at some point. Although I don't wish them that, but this might be a reality that we will face soon enough. So how I ended up, I don't know. It's just my probably my specific thing. I just like optimizing the code that I'm working on, and this is how I got into the profession. in doing those kind of low level tunings. Yeah.
So you get really happy when there's 1 microsecond win in your code.
Well, yeah.
Well done. I think it's amazing. Well done.
Indeed. Denis, I have just a question for you about some of the sort of the early positioning statements you made there about the general Moore's law trends and the quote from Hennessy from 2018 about sort of the death of general purpose computing. I'm curious how you feel about that statement from Hennessy in 2021. Do you feel that that's aged well? And do you think that Hennessy would still say that?
I would say yes. Yeah. And then so and the reason why I think so is that and in general I believe we are at the starting of a new computing era. It may sound epic, but so it's more of post cloud era. Okay, so why? Well, because now we have a whole bunch of accelerators in the world, right? So you see, for every new workload, people are CPU is not the best choice, right? For every workload, right? This is the reason why we have VPUs, TPUs, NPUs, and the whole bunch of other PUs. So and there is actually a challenge for us for software developers, right? Well, why? Because it's hard to program heterogeneous devices, okay? And soon enough we probably well, not all of us, but some of us will be forced to program heterogeneous devices, okay? Like graphics, GPUs, NPUs, VPUs, whatever. We will not know where our code will run, so we will need to write some kind of heterogeneous software, and this will actually require to shift the paradigm of how we program, of how we write our code nowadays.
Understood. I guess the reason that I have some sort of cognitive dissonance on that is it's not from the point of view where you're coming from, so the programmer who is looking at the platforms that are available to program on, right? You're not looking at the offerings of 500 startups that are all working on their own new little accelerator that they hope will be the next big thing, right? Which has a very low chance of actually happening. What you get to see, and what we all get to see when we're developing is, for example, the ARM platform with the Mali GPU, right? So you see the thing that makes it into the mainstream that we can all program on, right? And the number of that's where I'm sort of I am a former semiconductor and accelerator developer kind of person, right? And it's so difficult. In fact, when I look in the last 5 years, I see huge amounts of venture capital that went into funding 500 different deep learning startups, all of whom are going to kill each other. They're all going to die because they're chasing the same small number of markets. And in fact, actually, the only two that have succeeded out of the 500 that I've heard of are Nirvana and Habana, and both of those survived not by having a successful product in the market that competed with NVIDIA or anybody else. They survived by being bought by a dying giant. They got bought by Intel, right? That's the only way to survive as an accelerator maker, a startup. So Hennessy may be right, and yet that's not advice that applies to anybody who would try to build a little company that would do what his company in 1984 tried to do, right? MIPS. Anyway, it's just a strange dissonance at the two ends of the food chain. The prognostications are just completely irrelevant to each other, the opposite sides. But anyway, I agree with your points, and it's interesting to see the implications on both sides.
Yeah.
All right. So any other questions? We have 1 minute left for the Q&A of Denis. Dane, no. Denis. All right. All right. So thank
Good
you,
talk, guys.
Denis. It was a great presentation. Thank you for building that content and sharing it.
Thanks for having me. It was a pleasure.
You've been more than an honor. And that's also, I think, like I mentioned before, it would be great to have a detailed blogs because you have a lot of references in your presentation. So with all those great links, that will be very beneficial for our community. So that will be great. So we're looking for this blog. It will be great.
Thank you very much.
Well done.
All right, Denis, and enjoy your day. And so it's now 11 a.m. So the next performance rockstar will be Lloyd in 15 minutes. So we will have a short break of 15 minutes, and we'll get back with the last speaker of the Eastie Boys stage.
Thank you, Henrik.